sorry, I'll start again. Now, somebody just told me recording in progress very loudly in my ear. So welcome everybody to this first software seminar series organized by CCP5. Paola has told me we are still CCP5. We are not quite yet CCP5++. For those of you that don't know, CCP5 is the UK's computational collaborative project on condensed phase simulations, and that project will be entering its next phase, renewed by the EPSRC in the autumn, revamped slightly as CCP5++. And as part of the activities of that network, I have been volunteered by Paola, who is the chair of CCP5++, to develop a UK simulation roadmap for software in the area of condensed phase simulation. So my first thoughts on that were it's difficult to develop a roadmap unless you know where you are already. So we thought we'd put together this seminar series to try and gain a bit of understanding about where in the CCP5 community different software packages are being used, what functionalities are people relying on, what is the diversity of software solutions that are out there, what problems are people trying to solve, and how do particular software packages or things that are developed within people's own research groups address that need for capability and provide that functionality, and maybe find some commonalities and think about where we could maybe work together to seek perhaps some funding for new functionality that the community needs that we don't currently have going forward. So I'm very pleased to say that our first speaker in this series is Matteo Salvalaglio from University College London. So Matteo obtained his PhD in chemical engineering in 2011, which doesn't seem like long enough ago, in Italy at the Politecnico di Milano. And then he did postdoctoral work jointly with Michele Parinello and Mazzotti in ETH Zurich, working on enhanced sampling of molecular dynamics simulations, something which I'm sure he'll tell us quite a bit about today. And then since 2015, he's been at University College London, where he's now an associate professor leading the molecular modeling and engineering group. So Matteo is going to tell us a little bit about the software that he uses to perform these kinds of enhanced sampling simulations and what he can do with them, what the capability of that software tool set is. If you do have questions during Matteo's talk, do feel free to ask them using the Q&A functionality in Zoom, which we're not allowed to use Zoom at my university, so Zoom is very new to me. The Q&A button is at the bottom if Zoom is also new to you, and I will interrupt Matteo with any questions that people raise via that mechanism as we go along. And of course, there'll be time for questions at the end as well. So without any further faff from me, I'll hand over to Matteo. Matteo, thank you very much for giving this first seminar.
Thank you, David and Paola, for inviting me for this talk. And so, as David mentioned, this is the first of a series about software. So I don't know if I pitched my seminar correctly here. What I would like to do in this seminar is to basically discuss one particular software that we are using in our research, the molecular modeling and engineering group at UCL, which is Plumed, and show how that fits in different tasks that we need to carry out in order to perform our research. So to do so, basically, I would like to start by discussing what is the aim of our research and what is the context in which we're using this type of ideas and software. The main objective of our group is to use molecular modeling to understand materials assembly. And in particular, we want to be able to construct a rational link between the structure of molecules, of the building blocks that come together forming materials, and the properties of these materials. And in order to do so, one needs to be able to understand how these building blocks actually come together forming crystals, and how in these assembly process, they develop a specific bulk structure, but also how these processes lead to the growth of macroscopic particles that exhibit specific morphology, and how the interplay between structure and morphology actually plays out, defining the properties of these materials. So this is the context in which we perform molecular simulations. And as a context perspective, I would like to mention the fact that we use mostly classical molecular dynamics simulations. So all the results that you're going to see and the context in which I will mention plumed is related are related to classical molecular dynamics simulations. So in this context, as I mentioned, plumed plays a huge role. And I will try to discuss 4 aspects in which we are trying to use, we use this code. And in particular, these 4 aspects touch on 4 particular needs that are necessary in order to sample the assembling growth of molecular materials in realistic conditions. So the first point will be related to investigating the self-assembly events, using bias sampling. I will mention briefly what I mean by self-assembly event and why bias sampling is useful and what is the role of plumed in this context. The second point instead is a bit less usual, which is how can we use plumed, or in general a code that allows for introducing forces as a function of the position of the atoms in the system in order to mimic experimental conditions, in particularly referring to open boundary conditions in finite size simulations. Then I will go to how we can use these ideas to detect assemblies in a systematic manner in solution. And here I will mention the identification of ion clusters in the double layer close to graphite electrodes. And finally, I will try to show how you can extrapolate information also about finite temperature crystal structures of organic crystals. So one of the most important aspects of using a software is giving credit to the people that develops the software. So in order to avoid forgetting at the end, I want to do it right now. So plumed is developed by 4 main developers. That used to be 5 when it was published, when the latest paper about plumed was published in 2014. And these 4 or 5 people that are driving the development of plumed are Gareth Ribello, Max Bonomi, Davide Branduardi, Carlo Camilloni, and Giovanni Bussi. And they deserve the credit for having developed something that is so flexible that we can couple it with ease to many molecular dynamics engines. Another important development in the community that uses this software came a little bit later in 2019. There has been a white paper published that details how, as a community, we are aiming to maintain our inputs and details of our calculations transparent. So that initiative has led to the development of a repository of input files. So many of the things that I will discuss today are also mirrored and accessible on this repository that is called Plume Nest. And again, huge credit to the developers and the main people in this community that is driving the development of these 2 initiatives. A particular mention, which is important in this context, goes to Gareth Ribello, who's one of the core developers, but is also the person that's mostly responsible for the development of the functionalities that we use to perform the type of calculations and the type of tasks that I will describe mostly during my seminar. So Gareth is the hero here, and the person that has really implemented very flexible ideas and methods within Plume that allow us to do easily what I will describe. Okay, so without further ado, I will jump into the first point. So investigating self-assembly events with bias sampling, which is the aspect in which Plume plays a role that is probably the most familiar for people that has been using in unsampling simulations or bias sampling in some form. So typically, when we are interested in sampling nucleation events, what we are interested in observing is something like the trajectory that I'm showing in this movie. So we're interested in observing the formation of a new phase from a parent phase, And the new phase has a composition and a structure that is distinct and different from the parent phase. So in this case, you're observing the formation of a crystal that emerges from a supersaturated solution. The supersaturated solution is a multi-component system. Here, the solvent is not shown for clarity. I'm only showing the solid molecules. And the point with studying this type of processes is that these processes are associated to an inherently high free energy barrier. So the formation of this new phase in the core of in the bulk of a parent phase is always associated to an energetic cost that materializes into a free energy barrier that typically we represent with classical nucleation theory. So if we look here on the right, I'm representing schematically what happens in terms of free energy associated to the formation of a cluster. Here, NC represents the number of atoms or the number of constitutive elements that make up this cluster. So basically the size of this thing that's growing in solution. And on the y-axis, we have the energetic cost associated to the formation of this cluster. So typically in macroscopic conditions, we have a high free energy barrier that is due to the fact that we have a free energy cost associated to the formation of an interface for this cluster. And overcoming this barrier with unbiased sampling is impractical. So basically, we can always think of a system that has a barrier that is significantly higher than, that induces a characteristic time for the observation of a nucleation event that is much larger than the time we can afford to sample explicitly in our simulations. An additional problem that we have in small-scale simulations, especially when they entail a multi-component system, a multi-component parent phase, is the fact that since they're very small, the size of the cluster is coupled with the driving force associated to the formation of a new phase. And this actually leads to a distortion, which I'm representing here with this shift from the green curve to a red curve here. So this distortion in the free energy profile here is quite dramatic. I'll show you another example when it's smaller, but the point is that this type of distortion is due to the fact that we are dealing with simulations that are at finite size and with a finite number of atoms. And in these simulations, we have no compensation from the driving force while the cluster is growing. This leads to a distortion that makes the event that was already a rare event even more rare, so even less likely to occur within a fixed simulation time. So a typical approach to overcome this problem is basically associated to using enhanced sampling methods. And the application of enhanced sampling methods is based most often on the definition of collective variables. So I will discuss a bit here how metadynamics solves this sampling problem. Metadynamics is not the only enhanced sampling method that can be used, but most enhanced sampling methods, even those that are not associated to the introduction of a bias potential, actually require the definition of a collective variable or the definition of a proxy for a reaction coordinate anyways. So many of the things that I will tell you about Plume, an application of Plume in this context, are quite general. So going back to metadynamics, the idea here is that basically whenever we have a system in which two interesting metastable states, let's call them A, are separated by a high free energy barrier, basically we can introduce a bias potential in order to facilitate the escape of a system from one of these metastable states. Metadynamics does it by basically constructing an adaptive bias potential that increases the free energy of the state that we are sampling, and also increases the fluctuations of that particular state, and induces the exploration of the configurational ensemble for that particular system. Now, the important point that I mentioned at the beginning here is this x-axis. So on the y-axis, in these representations of these two metastable states separated by a high barrier, we have free energy, which is a measure of the cost associated to these transitions and of the probability of observing this transition. The higher the barrier, the lower the probability of observing a transition. However, on the x-axis, I haven't defined what this collective variable is. So this collective variable is typically a function of the coordinates of the system, and it's a proxy for a reaction coordinate. So it's an approximation of the reaction coordinate associated to a transition between the two metastable states, here represented as A and B. So the first application of CUMD in this context, in the context of investigating self-assembly and nucleation and growth also from solution, is in the definition and application of collective variables in order to bias the exploration of configurational of the configurational ensemble for molecular models. Metadynamics also allows to recover the free energy. I will have a slide later that shows that, but the focus I want here to be on the collective variable side of things. So in order to do that, I'd like to use an example that comes from investigating the nucleation of urea within its melt. So if we look at a liquid phase constituted of urea molecules, actually this is a complicated system. In Cartesian coordinates, we cannot really tell whether there is any ordered domain within this system. And essentially, we are looking at a system that is inherently high dimensional and not human readable. So what we can do is basically define functions that are based on the local density and local order of the molecular environment that in which individual urea molecules are embedded. And using these functions, we can define a collective variable that describes the state of the system. So in this case, in particular, by using functions that represent both the density and the order around each urea molecule, one can easily identify what is the character of each urea molecule embedded in a dense system. So in this case, for example, I'm representing urea molecules as sticks, and the bluer the color, the higher the value of this gamma I scalar that represents the state of each urea molecule. And the more ordered the environment, so the more crystalline the environment it is. Now, these functions that are based on representation of the density and order locally for urea molecules are functions of the coordinates of the system. And the CUMD in this context plays the role of computing these functions and computing their derivatives in order to apply forces that allow us to, for example, to use metadynamics, or for example, also other biasing methods like umbrella sampling or steered MD or other methods similar to this one, to these ones. The representation that I'm showing here is based on a specific formulation for these local density and local order functions that is not particularly important. It's described in detail in this paper here, but the idea here is very general. And actually, CUMD allows to compute collective variables that are based on this idea, to compute a wide range of variables that are based on this idea. Examples are like the Steinert order parameters, but also the potential energy of the system, the entropy, or the information entropy for molecular systems. So basically here, CUMD provides a framework to compute collective variables, compute their derivatives, and therefore introduce a bias in the system. When this is achieved, one can actually obtain the sampling of these very rare fluctuations, like the formation of an ordered domain from a disordered liquid. And here, what CUMD is doing is represented from in this scheme that comes from the CUMD paper, in which basically, after initialization, the atomic positions are passed to CUMD that computes these collective variables and their forces, and then passes back the forces to the integrator that is typically contained in an MD code. So the flexibility here of this CUMD package is the fact that it can couple easily with a lot of different popular MD codes, and the type of tasks that carries out are independent from the MD code for the specific choice of the MD code. Clearly, performing this type of analysis also allows to discover new states, compute thermodynamic properties of systems. Here, I'm showing just an example of these type of ideas based on these local density and order collective variables to investigate phase transitions in CO2 under pressure. And I'm introducing this example because basically what I want to drive home is that this type of approaches also allow to discover states that were not a priori defined when computing and defining the collective variable space. So here, this collective variable space has two variables that are maximized by two ordered phases of CO2. However, in the sampling, we discovered that there are also defected configurations sampled in this space, and we can actually compute free energy differences between the different local minima in this free energy surface as a function of pressure. And we discovered, for example, that for high pressures, this state becomes the most stable one instead of the state that doesn't contain any defect. Okay, so this was the most intuitive and perhaps common way of using CUMD in the context of this type of material simulations. I'm saying common because it resembles a lot the way CUMD and biosampling is used in other contexts, like in biomolecular simulations. There are other aspects, though, that play a role. I mentioned earlier that whenever we are performing assembly simulations in a finite-sized system, basically we are looking at a system that is distorted, or a free energy surface associated to the process that is distorted with respect to the macroscopic one. So here I would like to discuss how conceptually CUMD allows to overcome this problem by introducing ad hoc forces that are basically able to mimic an open boundary system. So the problem again is associated to the depletion of the mother phase. So, and it's represented by these two free energy surfaces here. So in a macroscopic system, we have that the free energy associated with the assembly process resembles this typical classical nucleation theory shape. In a finite-sized system, instead, it has this different shape. And therefore, we would like to be able to remove this limitation, remove these artifacts due to finite size. And again, this second point is aimed to clarify how we can use CUMD in this context. So the approach that we have developed a few years ago, I'm saying we very generously here, because the person that drove the project is Claudio Perego, who is now working between Switzerland and Italy, is called CUMD. That stands for Constant Chemical Potential Molecular Dynamics, and is based on the idea that we can use this flexible approach that CUMD allows to introduce forces in a system such that are able to maintain the concentration of solute molecules in a bulk, in a certain region of the simulation box that represents the bulk, constant. So in order to describe the method, here I'm looking at a schematics of a system that has a crystalline phase here, that is characterized by a certain thickness and the position of an interface that is identified by Zi, and then a liquid phase here that is characterized by two regions. One is this transition region where the concentration relaxes to a bulk value, and then a region that actually represents the bulk of the system, which is indicated with where the concentration is indicated with NB. Now, in this region, if we were dealing with a macroscopic system, the concentration would be constant, because at this scale, the rate at which a crystal growing is subtracting molecules from a bulk solution is so low that would not affect the background concentration. Essentially, if we're thinking of investigating a macroscopic system, the background concentration of our supersaturated solution would not change. However, whenever we start looking at finite-sized systems, so if we encase this system inside a molecular simulation box, we realize that if the interface starts to grow, the concentration in the bulk starts to decrease, and we observe that the growth process cannot be modeled at constant driving force, so against a constant concentration of solute molecules. So CUMD allows to overcome this problem by introducing artificial forces that are based on the same idea of the collective variables that I discussed a while ago. So basically, those forces are defined as a function of the position of the atoms in the system. CUMD is based on defining some additional regions. One region that is defined is called controlled region, which is the region in which we aim to maintain a constant composition of the liquid phase. Then there is a reservoir that acts as a physical reservoir for the system. So a region in which we are not really interested in investigating any molecular level phenomena, but we are just storing solute molecules. And then a region here, which is indicated by this green shade, on which these F mu forces are applied. Now, these F mu forces are harmonic forces that are based, in which basically we have a force constant K that multiplies the difference between the instantaneous value of the concentration in the controlled region, which is indicated by NICR, with a reference value, which is called N0I, which is the target value that we want to maintain constant in this control region. And this harmonic force is multiplied by a function G that is a function of this space, of this coordinate Z. So it's a function actually that localizes the application of these forces to atoms that fall within this green shaded area. Also, the concentration in the controlled region can be computed as basically based on the position of the molecules. In particular, we can define a function which is defined, in this case, is defined piecewise, and it's 1 if the position of a molecule is within this control region and 0 otherwise. So basically, the concentration, this formulation allows us to compute the number density of the control region based on the position in Z of the atoms of the system. So by putting together a system that works in this way, whenever we have in this case, an interface that is depleting the reservoir of molecules in contact with it, we also have a system that is able to replenish this control region and is able to mimic the evolution of the crystal interface against a constant concentration background. The point is that this is a different application of the flexibility allowed and enabled by Plumed, but it's based on very similar principles, because once again, in this case, Plumed is used to apply those forces that are nothing else than function of the atomic position of the atoms in the simulation box. So just to show how this works in the case of crystal growth, here I'm showing again, this is again urea. This is a urea crystal slab that is in contact with a solution. It's the crystallographic phase of urea in contact with solution is the 001, which is known to grow following a rough growth mechanism, and therefore its growth rate is linearly increasing with concentration in the bulk. And here on the right, you have a reference case of a simulation performed with this configuration under normal NPT conditions. So basically, in this case, we are looking at this delta NC here, which represents the number of molecules that enter in the crystal phase that are incorporated in the crystal as a function of time. And X is the molar fraction of urea in the controlled region as a function of time. And this representation actually highlights why we have a problem here, because we have that growth happens at a constantly changing, against a constantly changing background concentration. So we're not really able to pinpoint what is the crystal growth as a function of the concentration in the control region. CUMD allows to overcome this problem. So in this case, you see a similar plots in which we are looking at the growth of the crystalline phase against the molar fraction in the control region. And you see that the molar fraction in the control region after an initial equilibration is maintained constant for a long period of time until it starts to decay. Now, this decay period is associated to the complete depletion of the reservoir. Clearly, if we have a physical reservoir, that reservoir is not infinite, and therefore, at some point, it runs out of solid molecules. But until that point, basically, the dynamics of the system takes place against a constant concentration background. And so basically, we can study what happens as a function of this concentration, of the value of this concentration background. So here I'm showing the same plots obtained for a higher value and for a higher value again. And basically, one can study what happens to the growth rate, taken as the slope of this green curve, as a function of the concentration in the control region that represents the bulk of the system, of the liquid phase for this particular problem. And the good thing is that this problem, in this case, is known to be dominated by rough growth, and we are able to recover a linear relationship between the concentration in the liquid phase and the growth rate, showing that basically we are obtaining what we were looking for. I want to basically turn around a second and show that one can get creative with this idea and actually use it to model also very different problems. In this case, I'm looking at the diffusion problem, and this is a collaboration that we developed a few years ago with Daresbury Laboratory, and the first author and main driver of this project was Aydin Ozgan, a PhD student in Osgur's group. So in this case, we are using this idea, but we are decoupling the control regions on the two sides of the membrane. And in this way, we are inducing a diffusive flux across the membrane. So this is the membrane, which is a MOF membrane. Then we have a transition region where there is a non-steady concentration profile, an inlet and an outlet control region that again are the regions in which we are controlling using Plume the density, the number density of solid molecules, in this case of gas molecules. And then we have a region in which the forces are applied and the reservoir. The point is that within the region that goes between the control regions and the membrane, there are no artificial forces introduced, and the dynamics in that region can be considered, I mean, it's only driven by the physics of the problem. So here you see that basically after a transient, one can obtain a steady flux of molecules across the system. And this is a setup that can be used to investigate diffusion across membranes. Oops. Sorry, I have Okay, there were key outcomes for this project that were, for example, the fact that we were able to control very tightly the concentration in the inlet and outlet regions, and also that in these conditions we were able to obtain steady state concentration profiles so we could sample for long times. And finally, the fact that this algorithm can be applied in order to maintain not just the concentration, but also the composition of the phases that are on the two sides of the membrane. So in a system in which one wants to model explicitly the competition between different molecules permeating through the same membrane, that's possible. Okay, so this brings me to the end of this second part, which is about basically mimicking experimental conditions using these forces that are defined using Plume. The third point is associated to detecting assemblies in solution. Whenever we are interested in investigating the formation of a new phase from a parent phase, we would also like to be able to automatically identify clusters and identify clusters based on some property that we want to identify in those clusters. So in this third point, I would like to give you an example of this idea, which is based on basically constructing an adjacency matrix for solid molecules in the system. Here below, you can see a schematic of this idea, where basically this is the adjacency matrix for this simple system of 10 points. And then by interpreting this adjacency matrix as a graph, we are able to identify the connected components of the graph as the clusters in the system. And by enumerating the number of elements or nodes that belong to every connected component, we are also able to identify on the fly the size of the clusters involved in the process. So in this particular case, we are looking at the formation of ion clusters in the double layer of an aqueous solution in contact with the graphite electrode. And this is a work in which we are also applying the CUMD idea that I just described above to avoid any depletion or deviation from electron neutrality in the solution bulk. This is the work that Aaron Finney has been performing in the group it's actually very timely that this is coming up today, because he's going to give an STMS seminar series 2021 seminar this Friday. So apologies for the shameless plug, but if you're interested in a lot more detailed results on this particular problem, that would be a great opportunity to listen about that. So here, what I would like to focus on is the fact that by controlling the concentration in the control region using CUMD, we're able to sample a large range of concentrations and to investigate the structure of the double layer in those regions. In all these cases, we're able to maintain steady state concentration profiles as a function of Z, which is the longitudinal dimension of the simulation box. And in all these conditions, basically, for concentrations that exceed the dilute conditions, essentially we're able to identify deviations from the expected profiles that can be obtained from mean field theories. So I want to summarize these results rapidly here to go then for the most important section, which is about the automatic detection of the clusters. So here I'm showing as A, B, and C 3 panels in which the concentration of ions is represented as a function of distance from the interface. And in panel A, we have not just concentration of ions, but also water, and both ions are represented together. However, in panel A, we also have only 2 concentration regimes. A diluted concentration regime that corresponds to the continuous lines, blue for Na plus and red for Cl minus, and the dashed lines that correspond instead to a slightly higher concentration regime. That it's interesting because it's associated to the inception of these non-idealities in the structure of the double layer. So if we start from the most diluted case, here we see that there is a buildup of Na plus ions close to the interface, and that the formation of this positively charged layer is followed by the formation of a negatively charged layer. To maintain the background of the concentration at a higher level, around 1 molar. Here you have that a more complex situation emerges. In particular, we see that the Na plus are still dominant close to the interface. We have the formation of a Cl minus dominated layer on top of it, but then as we move away, we have another region in which Na plus are in excess. Now, the emergence of these structures in the double layer becomes more and more important and prevalent when we increase concentrations. And this is shown in these 2 panels, B and C, where, again, these peaks associated to layers of different charge emerge as a function of concentration or disappear, as in this case here. This complexity emerging in the density profile of the ions as a function of distance is actually associated to a strange behavior, an unusual behavior of the double layer. And I mean unusual compared to the low concentration regimes in which we can apply mean field theories. In particular, we see that the double layer actually decreases in size with increasing concentration up to 1 molar. But then when 1 molar is reached, both due to the formation of these, basically to the intervention of these correlations between the position of the ions and the formation of structures as well in the double layer, the thickness of this double layer starts to increase again. So we have this non-monotonic behavior that is inherently associated with the formation of structures at the interface. And what we try to do now is to transform this observation into a quantitative estimate of the structures that are observed at the interface. So in order to do this, we start from this qualitative observation. For example, in this plot here is represented by the fact that the average coordination number between an NaCl close to the interface exceeds the limit of 1 that we observe in the solution bulk. And we try to use this idea of basically considering ions as nodes in a graph in order to obtain a quantitative representation of these structures. So in order to do this, basically, we identify ions in the double layer or in the bulk, and then we define an adjacency matrix, and then we perform a depth-first search algorithm in order to identify the connected components. Now, the number of connected components corresponds to the number of the clusters that are observed, and the size of the largest cluster, the size of the largest component corresponds to the size of the largest cluster. So I want to highlight once again how all the steps in this process are associated to defining functions of the position of the ions. So for example, identifying ions in the double layer, it's a task that can be performed by defining a switching function of the x coordinate as represented here. And the same is true for defining an adjacency matrix and so on. So this idea of using ions, considering ions as nodes in a graph and performing a search on the graph in order to identify components it's also relying on this flexibility that allows to compute functions of the position embedded in Plumd. And doing this actually performing this type of analysis allows us to bridge from a qualitative observation of this phenomenology at the interface to a quantitative analysis of the same process. So in this case, Aaron has very nicely shown how there is a discrepancy between the double layer behavior and the bulk behavior. So in this plot, which is quite dense, but I think it's really nice, you can see two groups of points. One represents the bulk, and it's represented by these squares, and one represents the double layer, which are these circular dots. And you can see that the squares in this plane, we are showing the number of clusters and the number of ions in the largest cluster. And you see that as the concentration increases, the concentration is represented by the color of these points, and the closer to red, the higher the concentration. The number of clusters increases as well. So there is an increase in the number of clusters in the bulk. However, the size of these clusters that are observed in the bulk is always very small. You see that there are basically, those are essentially dimers or ion pairs that are formed in the bulk of the liquid phase. What happens in the double layer instead is quite different. And you see that as concentration increases, so as these points go from blue to red, there is a deviation from the bulk behavior. And while the number of clusters increases similarly, what changes dramatically is the size of the largest cluster. So in the double layer, we see the formation of these significantly larger clusters that are reminiscent of the clusters that are observed as precursor to nucleation processes, also in the bulk at very high concentrations. So in concentrations that are much larger than those sampled here. There is another point that I want to make, that is that in this summary plot, we only show the standard deviation in the two variables and the average, but one can actually obtain the entire distribution for these quantities that is shown for three particular cases, X, Y, and Z, so at these three concentrations here. And in particular, this one shows how the two distributions in the bulk, which is the blue one, and in the double layer, which is the green one, are very different. Okay, this brings me to the last example that I want to make, which is essentially taking this idea of clustering structures and taking it from the Cartesian space where ions can be found, and basically bringing it to an abstract space of similarity between finite temperature structures. So here I want to show how we're using Plumd within a framework to identify polymorphic structures from finite temperature MD trajectories. So the context for this process, for this project, is the systematic reduction and refinement of lattice energy landscapes that are computed with crystal structure prediction methods. So crystal structure prediction aims at identifying what are the polymorphs of organic crystals starting from the molecular structure, and is typically based on computing lattice energies, so essentially potential energies of molecular crystals, without introducing explicitly the effect of temperature. Here we use molecular dynamics in order to introduce the effect of temperature in an empirical way. Essentially, we use molecular simulations as computational experiments in order to see what happens to the structure and whether the structure transitions from one polymorph to another, or it becomes unstable. So basically, the objective of this process is to start from a large number of points represented by this outer circle of many lattice energy minima, and to a smaller number of structures that are stable at finite temperature. And in order to do that, we need to be able to identify labile structures and structures that are actually able to transition from one state to the other. So in order to do that, we have developed a workflow. And once again, I'm using we very generously because the person in charge here is Nicholas, who's doing his PhD on this topic, and who has developed essentially a Python-based library that allows to implement this workflow, a workflow to apply molecular dynamics systematically to these crystal energy landscapes, even when we have a very large number of states in these landscapes. So there are many things associated to this workflow, and many things that I don't want to get into. I want to focus simply on the clustering idea. So taking a trajectory of a supercell and using plumed in order to define a metric to perform a clustering process. So in order to do that, basically we have chosen to represent the state of a finite temperature supercell, defining a fingerprint that is essentially a collection of probability density functions. And it's a collection of probability density functions that represent a structure by taking essentially, by representing the probability density of the distance between the centers of mass of the molecules in a system, represented here, and also probability density of important orientations between molecules, represented here for this is a qualitative representation for urea. If we have molecules that also involve conformational flexibility, we can extend this fingerprint to include also conformational degrees of freedom. And once again, in this context, plumed plays a role because we are using plumed in order to compute and output these probability densities that then can be treated both within plumed itself, but also outside plumed. And in particular, Nicholas has developed this library that allows to manage and use the fingerprints developed and computed with plumed to perform clustering. So once we compute these fingerprints, we define a measure of the similarity between different structures by computing the Ellinger distance, which is a function of the integral of the probability densities. And since we have different components, we take the absolute value of the, basically we take the modulus of these delta ij's computed for single fingerprints, and basically we are able to compute a distance matrix or a dissimilarity matrix between crystal structures. This dissimilarity matrix can then be fed to a clustering algorithm, and in particular we are using this FSFDP, fast search and find of density peaks algorithm developed by Rodriguez and Layo in 2014. So the idea here, again, I've said many things in a very short time, but the idea is We start from a static structure. We use MD simulations to introduce temperature, but then we find a problem. We need to find an objective way of identifying structures that are analogous at finite temperature. And we do that by essentially outputting probability densities of interesting degrees of freedom using plumed. And then we post-process all these things to reduce crystalline energy landscapes. Here I'm showing two results that we obtained for relatively small crystalline energy landscapes. In one case, it's urea. In the other case, it's succinic acid, which we obtain a 90% reduction in this case and a 75% reduction. But more recently, we have also worked on ibuprofen on a significantly much larger crystalline energy landscape, starting from 555 local minima and obtaining a 65% reduction of the size of these crystalline energy landscape while maintaining all experimental forms. Okay, so this brings me to the end. I've tried to cram a lot of stuff in this presentation, but the aim that my aim was to essentially show different phases and different aspects of how we can use a software like Plumed to complement and enable certain tasks in modeling the assembly of organic molecules, especially from complicated precursor phases like multi-component liquids. So the four things that I mentioned are basically enhancing sampling with bias, enhancing configurational sampling using bias sampling methods, mimicking experimental conditions. So in this case, mimicking open boundaries using things like CUMD, and then performing clustering in two different areas. One is the work that Aaron has been performing on interfaces, and basically it's based on identifying clusters on the fly from CUMD trajectories. And the other case instead is more abstract, is identifying clusters of finite temperature structures. And it's the work that Nicholas has been doing in the field of CSP. As I mentioned at the beginning, most of the input files and codes that we are working on are available under this Plumed Nest repository. And I think that's all. So I thank you for listening, and look forward to any question.
Okay, great. Thanks, Matteo. I'm not entirely sure if using Zoom in this particular mode of operation allows us to unmute ourselves and applaud, but on behalf of everybody, thank you, Matteo, for a very interesting talk. I couldn't help thinking quite a lot of the way through that if I wanted to do this kind of thing 10 years ago, I'd be looking at some absolutely awful mishmash of some simulation package, some little bits of my own Fortran code, some things I'd pulled in from Netlib, all glued together with a flaky bash script. And the fact that there are now open source software packages that are fully integrated and plugged directly into MD codes it shows that progress is being made in the right direction. I think it's very positive.
I agree, and I think that a lot of credit for this particular development should go to the development team of the package, in particular for these applications to Gareth Ribello. Many of the things that are related both to collective variables and to the probability densities of descriptors are coming from his implementation and development work. So yes, this note I think should be a badge of honor in his yeah, for him really.
Here. So do we have any questions from the audience for Matteo? Do you use the Q&A to pass those on to me, and I'll pass them on to Matteo. So maybe while people are thinking of things and typing them in, I could ask one or two questions. So can you give us an indication of how much overhead is involved in this? So if I'm used to screaming through a GROMACS calculation at tens of nanoseconds per day, and then I want to do this stuff on top of it, how much does that slow me down?
So the overhead so the overhead depends really on the complexity of the symmetry function that is used So first of all, it depends on the context. The area in which the overhead plays a bigger role is in the first point that I tried to discuss, so in the sampling of self-assembly events. And in particular, the overhead goes with the complexity of the symmetry function that is used to define that local density, and local order that I mentioned sometime in the beginning. So if the function is extremely expensive, like for example, in the case of Steinert order parameters, the overhead here can be significant because it's the implementation as of now favors flexibility over performance in this context. Instead, for variables that are just based on density, things have improved dramatically. I think in the last couple years, it's too recent, but I think in the recently with the different management of neighboring lists, the performances of density-based functions have improved quite dramatically. So the overhead on density-based ideas is not great. In the case instead of complex symmetry functions, yes, it can be limiting. In fact, there are cases in which we really are. This becomes the bottleneck for the feasibility of calculations. One in particular is one case that I have in mind in particular is the nucleation of conformationally flexible molecules from solution, where the variables themselves are so complex, basically imposing an overhead that does not allow to apply them on the fly to any problem, irrespective of complexity, essentially.
We have a question from Paola in the moderator chat, because the moderators apparently can't post in the ordinary chat. Are there any rules to decide on what collective variables to choose for sampling the free energy?
So there are some. So it depends. This opens up a bit of a kind of worm, right? There are different levels of accuracy that you want to have in order to be able to sample a free energy surface, and it depends really on what you want to get. If you want to get a free energy difference between states, it is essential that, for example, if you're looking at this free energy surface that I'm showing at the moment, where you have two different phases, it is essential that these two phases are not degenerate in the spaces of the CV. So that all the configurations that belong to phase 1 and phase 3 in this particular example do not overlap in the space of collective variables. So irrespective of which variables you're using, you want this property to be respected. It's a different and more complicated story if we're interested in computing a free energy profile that describes accurately the free energy associated to the transformation between phase 1 and phase 3 in this case. So in this case, again, we test the accuracy of the variables, or the appropriateness of the variables, on their ability in representing certain features, for example, the transition state ensemble of the associated to the particular transition, and therefore they might need to basically to obey to stricter tests. For example, one could perform commuter analysis in order to understand if a variable is good enough to represent features on the pathway. So I think there are these two tiers. If one is interested in free energy differences, the non-overlapping, it's a condition that's essential. If one is interested in pathways and in mechanisms, then the ability to capture features, it's important. So these two different tiers also involve a very different computational cost associated to verifying that the variables are actually fulfilling this type of requirements.
Okay, thanks, Matteo. We should wrap things up. So I'm trying to keep to time as much as possible in this seminar series. So I'll thank Matteo again for his interesting talk, and I will plug the next event in this software series, which is on the 17th of June at 2 p.m, where the speaker will be James Commode, my colleague here at Warwick. James, this is not Warwick, this is my living room, but my colleague at Warwick, James Commode, who'll be talking about the QUIP code, which is a code that can work with machine learned potentials and do various other fancy modern things. We are open to suggestions from the community for speakers in this series as well. So if you do have particular software packages that you'd like to hear about, and you would like us as CCP5 to invite people on behalf of the community, then do please get in touch with those suggestions. So with that, again, yes, thanks Matteo, thanks everybody for coming, and we will see some of you in the next seminar.
I thank you.